Guys, welcome back. So today we will learn about state assignment in asynchronous sequential systems, asynchronous sequential circuits. So as we know, in asynchronous sequential circuits, state assignment is mainly done to get rid of a condition called as racing. So racing is a simple condition when a transaction happens between, or when a transition happens between one state to another state. Let's say we have two states here, A and B. So we make sure that the transaction works in such a way that no more than one bit change is allowed. So we make sure that the transaction happens in such a way that when a state transition happens between A and B, or A to B, the number of bits that are changed in this transaction or transition is not more than one, or we make sure only one bit change is allowed. So this one bit change will help us to get the proper steady state at the end of this transition. If there is more than one bit change, then that is what we call it as racing. So we make sure when we assign the values to any states here, or assign binary values to the states, we make sure we don't get the racing condition. So being said, there are two ways in which state assignment can be done. The first one is shared row state assignment, and the second method is one hot state assignment. So in this video, we are going to focus on the shared row state assignment. So let's get started. So let's take an example of a float table which has got just two rows. So float table with two rows. So let me take an example. Let's say I have a small float table. Like this. So let's say we have just two states in it. So two rows, A and B, and the inputs are 0, 0, 0, 1, 1, 1, and 1, 0. So let's say I have A, B, okay, dash, and followed by A. So here let's say I have B and A. Okay. So in this scenario, we just have two states. One is A and another one is B. So if we randomly assign some binary values to these states, let's say I assign a value of 0 for A and value of 1 for B, then obviously there is no race condition and random fashion works fine here. So if we are having just two rows or just two states, then we will go for the random state assignment. Just any one state will take a value 1 and other state will take a value 0, because we are working with binary values. We have the maximum value of 0 and 1. Now the next category, let's say we have a float table with three rows. So let me take an example of a float table with three rows, and let's start analyzing that how state assignment could be done. So let me draw a float table. Here I have three rows, so we have three states here. So let's call the states as A, B, and C. So let's take an example of this float table. We have three rows, A, B, and C are the states. So I have three states here. My job is to assign binary values for these states, and the inputs are given, that is 0, 0, 0, 1, 1, 1, and 1, 0, and we have marked the steady states. Now let's take step one. So step one is to draw the transition diagram. So transition diagram just imitates this whole table. So let me have a state diagram here. So A, B, and C. So this diagram's purpose is just to understand the dependency of one state on the other and the transition between states. So we are not going to mention the inputs and outputs here. Just we will draw the transition from one state to another state. So if you take the first row, this is my present state and these are all my next states. So from A I can go to A itself. So there is one possibility. Then from A I can go to C. I'll put an arrow mark in this direction. From A I can go to A again, so that's already drawn. From A I can go to B also. So this is the transition from row A. So let's talk about the state B. So from B we can go back to A, so I'll make this bidirectional. From B, I can go back to C, draw this arrow. From B, you can go to A, which is already drawn, and B to B is also available. Similarly, the last row is C. So C to A is possible, yeah. And this is the first column. And C to C, we can take a self loop like this, and C to A, which is already drawn. Then C to B is also possible. So let's say A takes a value. This is a random assignment. Roll back. Now we have drawn the transition diagram. Let's assign some random values and find out whether racing condition exists or not. So let's say I am going to give a value of 0, 0 for A, and 0, 1 for B, and 0 or 1, 0 for C. So let's say this is 1, 0, this is 0, 1, and this is 0, 0. So if you just redraw the diagram with the help of the state values, it is 0, 0 for A, 0, 1 for B, and 1, 0 for C. I'm just going to omit this self loop because that doesn't end up with a race condition. So I'm just focused on the other transition. So I'll draw this. Also possible. We have just replaced the letters A, B, and C with the help of the binary values. That is in step 2. Now let's check whether we have a race condition here. Now let's analyze this transition first. So transition from 0, 0 to 0, 1. So if you see here, the first bit is 0 and the first bit is retained as 0. Okay, now. And the second bit is 0 here, whereas the second bit is changed to 1. So in this transition, we have only one bit change. Both the bits are not changed. The first bit is retained as it is, whereas the second bit alone is changed. So this is no race condition. We don't have a race condition here. Let's check the second one from B to C. So that is 0, 1 to 1, 0, and the other way around. So both are mutual. So from 0, 1 to 1, 0, I have a race condition because if you see, the first bit 0 is changed to 1 and the second bit 1 is also changed to 0. So I have 2 bit change here. So any change that is more than 1 bit is called as a race condition. Likewise, if you analyze the third possibility 1, 0 to 0, 0. So here the first bit is changed but the second bit is retained. So here also we don't have any race condition. So we can understand that there is a race condition that exists between the state transition between B and C. So when we transfer between C and B as well as B and C, we experience a race condition. Now how to solve this race condition? So we'll move to step 3. So in order to solve this race condition, we are going to introduce a new state. Let me introduce a new state called as D, and let's assign a value of 1, 1 because that is the last option what I have. Since I have 2 bits, the combinations available are 0, 0, 0, 1, 1, 0, and 1, 1. So all these 3 bits combination are taken. So I have only one more combination left out. So let's take that state as the newly introduced state. So we are going to introduce this new state between the states which experience the race condition. So we have a race condition between these two states. So let us introduce this new state between these two states and see and check again for the race condition. So let's draw the diagram again. So 0, 0, 0, 1, and 1, 0. So here this is called as A, this is B, and this is C. So if I want to go from C to B or B to C, I have to go through this new state. So let me state here. So this transition is not changed. A to B is fine. A to C is also fine for us. We are not going to modify that. But B to C is going to go through D. So if I want to move from B to C, I go to D, then I move to C. Similarly, if I want to move from C to B, I go to D first, then I go to B. So let's check the race condition again. So if you want the condition between C and D, nothing else but 1, 0 to 1, 1. So we don't have any race condition here because there is only one bit change. The first bit is retained and the second bit is alone changed. Likewise, if I move from D to B, so that is 11201. Here also the first bit is changed and the second bit is retained, so no race condition. So when you are introducing a new state here, the race condition is solved. So we have increased the number of states. So from 3 we have moved to 4 states here. So our job is to redraw the flow table again. So if you redraw the flow table, so let's draw the flow table again. So we have 4 states here: A, B, C, and D. So there is no change from A to C. So when we are moving from B to C, we have to do some modification. So the state A is retained as it is: A, C, A, B. So if you see the state B, if I show you the previous flow table, so from B I can move to A, from B I have to move to C, and from B to A, from B to B. So here this is a problem. So in order to move to C from B, I have to go through D. I'm going to modify that a little bit. So what I'm doing here is, from B, if the input is 0 0, then we go to A, there is no change in it. From B, if the input is 0 1, we are supposed to go to C, but in our newly formed state diagram we have to go through D. So I replace this with D, and for the same input from D I go to C. So I repeat it: from B I am supposed to go to C, but since we have introduced a new state D, which is intermediate between B and C, I write that here. And from D, for the same input 0 1, I am going to C. So internally, if you see, when I give 0 1 as an input from B, I move to D, and from D, if I give 0 1 again, I move to C. So likewise, the next cell is A, no problem, there is no change in, and the next cell is B, there's no. So when we are speaking about the row C, the first input 0 0 makes C to go to A, that is fine, and 0 1 goes to C, that is also okay. 1 1 goes to A, that is fine, and 1 0 goes to B. But if I give 1 0, I am not supposed to directly go to B, I have to go through D, so I mark it as D, and for the same input I mark it as B here. So from C, if I give an input of 1 0, I am going to D, and from D, if I give an input of 1 0, I am reaching B. So this is how you draw the fully formed or the newly formed flow table. So this is how we solve the racing condition here when we have 3 rows. Now let's take another example where we have 4 rows, and let's try to understand how we solve the racing condition there. So let's have an example flow table here which has 4 rows. So step 1 is to first draw the transition diagram to understand where the racing condition exists. So let me draw the transition diagram. I have 4 states totally, so A, B, C, and D. So from A I can go to C, A, B, and A. I can go to C, I can go to B. So the self loop, I'm just discarding that because that's not useful to find the racing condition. From B I can go to B, from B to C, and B to A is also possible. So B to A is possible, and B to C is also possible. Likewise, from C you can go to C, C, D, and D. So this is possible. So from D you can go to B, okay. From D you can go to A again, possible, and from D to D, so that's a self loop. So if you analyze this, let's take a random value. Let's assign some random value to find out whether we have any racing condition here. So definitely we should have racing condition because it's like cross dependent. So in step 2, if suppose I assign a random value of 0 0 for A, and if I give a value of 0 1 and 1 0 for C and 1 1 for D, then from A to B there is no racing condition because only one bit has changed. So 0 is retained and the second bit is changed. From B to C we have a racing condition, so it is from 0 1 to 1 0, so definitely we can say that there is a racing condition here. Likewise the other segments does not have a racing condition, but still we do have a racing condition here. So if you compare this with the previous example where we had 3 states, so in order to solve the racing condition we included a new state. That's what we have done in the previous example. So here also if I include a new state, obviously I have 4 states now. So if I include a new state, that will become 5 states, or in future if I need more number of states, it will be more than 5. So since it is more than 5 states, I cannot represent 5 states with the help of just 2 bits. So I have to go for 3 bits assignment. So I can just give a random value of 0 0 0 for A, and likewise 0 0 1 for B, so on. So I have to go with 3 bits. So in order to find out a perfect state assignment without any racing condition, let's draw a state tree and find out the possible states. So that will be your step 3. So in step 3 we will draw a state tree. So let's start from the state A. So let me call this state as 0 0 0. So from 0 0 0, the possible transition without any racing condition is I can have 0 0 1. So if you have 0 0 1, it means just 1 bit is changed from A. So this is a possible state from A. So let me call this state as B. And the other possible state is I can have 0 1 0. So here also if you see there is a change of only 1 bit from A. So let me call this new state as C. And the another possible change is 1 0 0. Apart from these 3 states, we cannot have any other possible transition. So let's say the other possible transition is 0 1 1, but if I have 0 1 1, I cannot go from 0 0 0 to 0 1 1 because I have 2-bit change here. So I'm just finding out a proper state tree which gives me a state transition without any race condition. So let me call this state as D. So let's say start exploring this tree in a much higher depth. So from B, what are all the possible state conditions which does not have any race condition here? So if it is 0 0 1, so I can have 0 0 0 is possible, but 0 0 0 is already explored, so let's call that as A itself. So further I cannot expand this branch, I will stop here. So another possible value is 0 1 1, that is possible. So another possibility is 1 0 1. So since these two are new states, we can call this as E and we can call this as F. Similarly, from C 0 1 0, I can have a transition to 0 1 1, and I can have 0 0 0, and the last possibility is 1 1 0. So 0 1 1 is already given as E. So 0 0 0 is already mentioned as A, and 1 1 0 is not explored, so we will have a new value called as G to it. So let's start exploring this D. So D, the first option is 101 is possible. I change just 1 bit, and second one G, or from 100 I can make it as 110. So this 101 is already explored as F, so I call this as F. This 110 is already explored as G, so we call this as G. And the last option from 100 is 000. It's nothing else but A. So this A cannot be explored further. So now let's start exploring this E and find out the possibilities here. So one possibility from E is it is 0 1 1. So if I just make 1 bit change, it is 0 0 1 is possible. And then I can have 0 1 0 is also possible. And finally I can have 1 1 1. We'll draw it a little bit closer so that we can expand further. So 1 1 1. So if you see this 0 0 1 is already explored as B, so no more expansion possible. So 0 1 0 is also C, so no more expansion possible. 1 1 1 is not explored yet, so we will call this as a new state H. So let's go for exploring F now. So if you have F, then the possibility is 1 1 1 again. Then we can have another possibility as 0 0 1, and the last possibility as 1 0 0. So 1 1 1 is already explored just now, we call it as H. 0 0 1 is nothing else but B, so no more expansion possible. 1 0 0 is nothing else but D, so D is already explored, so no more possible. So let's go for E. So if you have E which is already explored here, so I can just write it again. So if I explore E which is 0 0 1, I'm just repeating the other branch 0 1 0, and finally 1 1 1. So this is nothing else but B, this is C, this is H. So likewise A is already explored, so no more possibility. So G is a new one, so let's explore this G. I will have 1 1 1, is nothing else but H. So the second possibility is 0 1 0, which is C, and the last possibility is 1 0 0, is D. Okay, so speaking about C and D, it's already explored, so we cannot explore it further. Just H alone is left unexplored. So here also, if you see, I have 1 1 1. So let's go for G again. So if you explore G, that is again, I'll get the same value here, so which is nothing else but, let me draw 3 lines first. 1 1 1 is H, and 0 1 0 which is D, sorry, it is C, and finally I have 1 0 0 which is D. So likewise, if I explore F, already explored F, which is HBD, that's what I have. So one is 1 0 0 which is D, another one is 0 0 1 which is B, and finally 1 1 1 which is H. So D and B are already explored, so just H is left out. So here also D and C are already explored, H is left out. So let's start exploring H alone, which is the last child which is unexplored. So let me explore this. So if you explore this H, you will get 1 1 0, the first option, which is G, and then we will get 0 1 0, it is another option which is nothing else but, sorry, it's not 0 1 0, it's 0 1 1, which is E, and the final option is 1 0 1, nothing else but F. So these two are already explored, and even G is also already explored, so we can stop here. So if you see, all the leaves here are already explored leaves, there are no nodes which are left unexplored. So with the help of this tree, we can finally form the transition diagram again. So that will be the next step. So let's call it as step 4. So according to the base transition diagram, what we have is A, then we have B, then we have C, and finally D. So from A to B, so if I take, I'm just going to replace the values what I have in the state tree in this transition diagram. So A took the value of 0 0 0, so B took the value of 0 0 1. So A to B, there is no problem, there is no tracing condition. So if I want to move from B to C, so if you check B, so I will start here. Let me take another pen. So I will start at this point. So from B to C, I have to go through E and then I have to reach C. So C is 0, 1, 0. And D is 100. So if you want to reach B to C, so you have to go through a state called as E, which is 0, 1, 1. So I have a state in between called as 0, 1, which is E. Similarly, if you want to reach C to D, so C is here. If you want to reach D, then you have to go through G, and from G I'll be reaching D. So G is 110. So let me introduce that new state G as 110. G is a new state 110. So C to G, from G to is possible. So then we have this connection between D to A. So D to A is a direct connection. I can directly connect to D and A if you see here. So there is no state in between D and A. Let me draw that as single line. And if I compare the previous state transition diagram, the link that is left out is I'm yet to draw A to C and D to B. So let me go for A to C first. So if I want to create a link between A and C, I can have a direct link. So that is possible. So I can just put a line. So A to C. Similarly, if you want to connect D and B, so let's check the tree again. So if you want to connect D and B, so from D, I have to go through F. From F, I can reach B. So F is 101, which is supposed to be introduced between the states D and B. So let me draw a state F, which is 101. So likewise, B to A is also possible, and I think we are done. So if you see this new transition diagram, initially we had 4 states A, B, and C, and D. Now we have introduced 3 more states so that the race condition is totally solved. So for example, if we take any 2 states here, let's say I'm taking B and E, or if I want to move from B to C, I'll be doing B to E, then E to C. So B is 001, E is 011, C is 010. So if I check these two, I don't have a race condition because the first bit is same, the last bit is also same, only the second bit has changed, so only one bit changes here. Similarly, if I compare these two, the first bit is same, the second bit is also same, the third bit alone is changed, so here also we have only one bit change, so there is no race condition. So likewise, we can just compare all the other states, and finally we can understand that there is no race condition that exists. So the final job, which is yet to be completed, is to redraw the flow table. So that will be your step number 5. So if I redraw the flow table, so let me have the 4 initial states first. I can draw the newly formed flow table here so that it will be easier for us to link. So initially we had 4 states. So now we have introduced 4 more states according to your new state tree. So E, F, and H is introduced. Let's draw that also. So if you compare the previous flow table from A to C, so if you want to go to A to C, so according to the new transition table, so initially I had A to C. So A to C is a direct link, so there is no change in it. Similarly, A to A is fine. And the third cell is A to B. So A to B is also a direct link, no problem. And finally A to A. So the first row is okay. So speaking about the second row, B to B is okay. So B to C. So in order to go from B to C, I have to go through E. So B to C is through E and E to C. So that's done. Similarly, the third cell is B to B and fourth cell is B to A. So there is no change in it. Now the third row. So C to C itself. So no change in it. So let me write it down. And C to D. So if I have to go from C to D, I have to go through G. So C to D is through G and G to D. So likewise, the next cell also. So C to G and G to D. So speaking about the last row, D to B. So D to B happens through F. So D to B is through F, from F to B. So it is D to F, F to B. So likewise, the next cell is D to A. So D to A is direct link according to the new transition table. So I just fill up as it is. Now the third cell is D to D itself. So I just keep it as it is, no change in it. So the other cells are not used. We can just put it as don't care conditions. The last state is not at all used. Maybe you can even discard this state. So this is the newly formed flow table, which is the updated flow table without any race condition. So likewise, for any number of rows, you first identify the transition diagram. With the help of the transition diagram, identify the states which has the race condition. Then with the help of the state tree, bring out all the possible states, and then we can assign those states. And this state tree will help us to transition between any two states. With a newly formed state transition diagram, reform the flow table, which is an updated flow table. So this is how we do shared row state assignment. Hope it is understood. If you have any queries, please do post in the comment section. We would like to answer that. I'll see you in the next video. Thank you.